All right, in this lesson, let's talk about bagging and boosting. Bagging is used when you want to reduce variance. The idea is to create several subsets of data from training samples chosen randomly. Each collection of a subset of data is used to train the decision trees. As a result, we end up with an ensemble of different models. When bagging with decision trees, we are less concerned about the individual trees overfitting the training data. The individual decision trees can grow deeply. The trees are not pruned. These trees will have both high variance and low bias. In our example, several base models execute different bootstrap samples and build an ensemble model that averages the results of the weak learners. Boosting is another ensemble technique used to create a collection of models. In this technique, models are learned sequentially, with early models fitting simple models to the data, and then analyzing the data for errors. Recall that with bagging, we had to run each model independently and then aggregate the outputs at the end without any preference to the model. In other words, with boosting, we fit consecutive trees at every step. The goal is to solve the net error from the prior tree. Unlike bagging, boosting is all about teamwork. With each decision tree, the weak learner dictates what features the model will focus on next. When an input is misclassified, its weight is increased, so the next decision is more likely to classify it correctly. In our example, in our case a decision tree, is trained on a dataset. On the model's first iteration, the weak learner makes a prediction. However, its accuracy isn't that good. Recall that's the very definition of a weak learner. Once the first iteration is completed on the training dataset, it's updated based on the previous results. In the Titanic dataset, the root node was split on sex. More specifically, was the passenger male or not? If we were using a booster, that split might have produced a shallow tree. These shallow trees are often referred to as decision stumps. Gradient boosting is a machine learning technique for regression and classification problems, which produces a model in the form of an ensemble of weak predictive models, typically decision trees. It builds the models in a stage-wise fashion, like all other boosting methods do, and generalizes them by allowing optimization of arbitrary differential loss functions. Gradient boosting involves three core steps. The first step that is required is that a loss function be optimized. That loss function must be differentiable. A loss function measures how well a machine learning model fits the data of a certain phenomenon. Different loss functions can be used for speech or image recognition. The second step in gradient boosting is to use a weak learner. In gradient boosting, the weak learner is a decision tree. Specifically, regression trees are used to output the real values for the splits, and whose output can be added together, allowing subsequent models' outputs to be added to the correct residuals in the predictions of the previous iteration. The third step is combining many weak learners in an additive fashion. Decision trees are added one at a time. A gradient descent procedure is used to minimize the loss when adding trees. That's the gradient part of the gradient boosters. Gradient descent optimization in the machine learning world is typically used to find parameters associated with a single model that optimizes some loss function. Gradient boosters are meta models consisting of multiple weak learners whose output is added together to get an overall prediction. The gradient descent optimization occurs on the output of the model and not the parameters of the weak models. Let's take a look at this process pictorially. In our example, you can see that gradient boosting adds these submodels incrementally to minimize the loss function. Earlier we said that gradient boosting involved three main steps. In our example, the weak learner being used as a decision tree. Secondly, the trees are added sequentially. And lastly, with more iterations, the error of the model is being reduced.